Okay, everyone. Welcome back to this course on logic. Can everybody hear me? Would you say yes? Maybe no one can hear me. Okay, so I will assume that people are okay. Okay, so we are, where we are. So we are in the middle of showing undecidability of validity questions in validity problem in personal logic. And we almost finished the proof was constructions about how this proof of the undecidability of this validity question. And our idea was to use reductions. Okay. And then the kind of reduction we were using was that we want to reduce the problem called PCP into personal logic, the validity question in personal logic. And then this PCP question was like this. So we are given a sequence of a set of tiles. Each tile is nothing but a pair of 0, 1 sequences like x1, y1, x1 may be 0, 1, y1 may be 1, 0, 1, and so on. So we have a finite set of tiles. And the question of PCP is to check or to show whether there exists a sequence of tiles, let's call it I1, I2, up to IM, where, because it's a sequence of tiles, each IL is an element from 1 to K. So, and then there are just some repetitions in the sequence. And then the sequence has to satisfy the following property, which is that if we collect the first elements of all the tiles in the sequence and put them together, then that should be the same as putting what we obtain when we do the same thing for the second component of the tiles, which means that the xi1, xi2, and I2 up to xim, same as yi1, yi2 up to yin. And the question of PCP is whether there exists such a sequence of tiles or not. So this is the question, and answering this is what this problem is asking for. And it turns out this is an undecidable problem. There is no algorithm that takes this finite set of tiles and answer these questions about existence of this matching sequence of tiles. Okay, so then our goal was to encode this problem into personal logic. And to encode this problem in personal logic, we said we're gonna think about signature. That signature will contain constant symbol E, which represent empty sequence, and also unary function symbol F0, which represent sequence of length 1, which contains 0, F0 and F1. That's a element, the Boolean element 1. And then we have a ternary symbol predicate P, and a binary predicate P. Okay. So this is a unary function symbol, both of these. And then this is a binary predicate. And then so actually whenever you encode some problem into logic, either in personal logic or in propositional logic, you have to have some interpretation in mind, okay? Which means that if we can construct a term in this according to this signature, and we should clarify what each term should mean. And in this case, each term should mean a sequence of 0 and 1. So the kind of term that can be constructed here is going to be, I mean, if it's a closed term or ground term, it will be an application of F0 and F1 and so on, maybe F0 to the constant E. And our intention is we want these two means, well, it is to intuitively represent a sequence which starts with a 0, 1, 1, 0. Okay, so it's coming. This sequence coming from this index 0, 1, 1, 0. So that's why we introduced a new symbol. So maybe different color is better. So this is our intention. So we introduced a new symbol. The symbol was to say exactly this guy. We introduced some macro. The macro was written like this, but this should be understood as multiplying the 4 function symbols to the constant symbol E. Okay. So whenever we write f of xi, because xi is a sequence of 0 and 1, that's should be expanded into this sequence, this repeated application of 0 and f0 and f1. Okay, according to this convention, here's our encoding. Then our encoding consists of 3 parts. It's one formula f1, the second f2, and f3. In a sense, f1 and f2 say they, in a sense, express P does the right thing. In other words, P express what we want to express. And then F3 say there is a solution. I mean, this one really intuitively say there is a solution to a given PCP problem. Okay, so now to understand this, we need to, I want to give you a reminder about what P is supposed to mean. So P is a binary predicate, so it's going to relate P and some T1 and T2. Especially we are interested in the ground term case, so maybe it's better to just write a ground term. Erasure. Okay. So we are interested in the ground term. So the ground term will be x. So x is a sequence of 0 and 1, which will be expanded according to this macro expansion. E, and then the f of y and e. So then this x and y are 0, 1 sequences. We intuitively, we want f to express the following fact. If f relates these two ground terms, this is not a formal definition, but intuitively we want this happens if and only if there exists and x and y can be produced by putting a sequence of tiles. Okay, so there exists some sequence of tiles, I1 up to IM, such that if we take all the first elements, that's same as x, x, I2, so on, x, I, M. And then if you put all the second element, that's same as y, I1, yi2, yin. This is different from the solution of PCP problem. In the PCP problem case, we are interested in whether what we obtain for the x part and what we obtain for the y part are the same. Here we are not really saying this. We are just saying x and y should be producible by putting a sequence of types. Okay, so that's our intention. And then the formula F1 and F2, in a sense, say that P does the right job in the sense this really is true, precise, not almost when this if and only if condition is true. Okay, so let's look at the definition of F1. F1 say if we can produce, so any So for every tile, so there are k tiles from 1 to k, and any pair of sequence in each tile, the terms generated from the sequence is related by p. So x1 and y1, which is coming from here. So x1 and y1, which is coming from here, they have to be, so p should relate these two guys. Then and x2 and y2 also should be related by p. xk and yk, if we generate terms, corresponding terms, which is f xk e f yk e, they also have to be related by this predicate symbol p. So this f1 really talk about the base case. Okay, what are what kind of matching x and y that can be produced by a single tile? F2, in a sense, talk about inductive case. It say that for every UMV, which represent a pair of sequences, which can be produced by a sequence of tiles, we have UMV, if they can be produced by a sequence of tiles. So then adding ith sequence, ith tile to the beginning of this UMV, there will also be a matching sequence. Okay, what does that mean? If we have, for instance, the f of x1 e and f of y1 e, that will be related by p because of f1. But then there's a second condition say, now if we put f of x2 and f of y2 to the beginning of this sequence, we concatenate them, they will continue to be related by p. Okay? So they say what we obtain, the conclusion side in this case is that specific instance of the conclusion is if we put f of say x3, let's call it to the beginning of this matching two terms, and f of y3 to f of y1 and e, that will be continue to be related by p. Okay, that's what this condition is saying. So in a sense, f1 is like a base case of the inductive construction, which we can use to produce a matching sequence. f2 is an inductive case. Okay, and you can kind of see that with f1 and f2, we cover, all the inductive constructions. We capture our intention about p, which is written as this if and only, okay, using f1 and f2. So now what this proposition says is that p has a solution if and only if f1 and f2 implies f3. In other words, this f1 and f2, this hypothesis that if our binary predicate p captures our intentions, so then there should be a solutions about this. Okay, so that's what this encoding is telling us. Then I want to go more details and then want to do the proof. So at the end of the last lecture, I asked you to think about the proof. So here's the proof about this. All this. Okay, how does the proof works? Okay. So we first prove the easy direction, which is this direction, which say f1, and so that's validity implies existence of solution. So say assume f1 imply f1 and f2 imply f3 is valid. And we want to show that there is a solution to a given PCP problem. So how to do it? And the key idea is to construct a particular, because the validity means this implication is true for all structure. And we want to just pick particular structure in such a way that if this formula is true in that particular structure, that implies this PCP problem has a solution. So we just want to pick a particular good structure. Our proof strategy is to pick one particularly good structure. Structure A, and use the fact that A satisfies F1 and F2 implies F3. Okay, so this is just general strategy. Then how to build this particularly good structure. So here's how to build A. So A is going to be a Hilbert structure. What does this mean? This means that interpretation of the constant, the underlying universe is fixed. So underlying universe is a set of all the ground terms. Which means that this one will contain constant E, and for, so essentially F1, E, maybe F0, 1, E, and so on. So essentially what we have is Fxe for all X is a sequence of 0 and 1. And this means finite sequence of 0 and 1, we have this term. So this is a representative form of any element in this underlying universe. Okay, so that's the underlying structure, and constant E, its interpretation will be just itself. Function symbol F1, its interpretation will be, so if we have a term T, it's going to be just putting F1 inside the term, in front of the term T. F0 the same, here to term T. Now, but what Hilbert structure doesn't tell us is, it doesn't tell us how should we interpret the predicate symbol. So this part is all fixed. But what's not fixed is what I'm going to describe here. So we now have to describe a meaning of binary predicate, which has to be a relation on A, so which means that it's a subset, it's a set of pairs of elements in the underlying universe. And it's up to us. What kind of PA we're going to use, it's up to us. And here's how we define this. We say that PA is a set of pairs, but this pair will contain, Fx of E and Fy of E only when there exists X and Y. These are the sequence of 0 and 1s that can be produced by a sequence of tiles. There exists I1 to some IM. These are the indices for tiles such that X is the all concatenation of all the strings, well, all the 0, 1 sequences in these tiles. So it's xi1 to xim, and y is obtained by yi1 to yin. Okay. Now, if you do this, then here's what happens. If we do something like this, then this, by assumption, because it's valid, we know this F1 and F2 implies F3 is true. But furthermore, A, so this is from assumption. But by our definition, this A satisfies F1 and F2. In other words, A satisfies the assumption of this implication. Why is that? F1 is really saying that any pair of 0, 1 sequences producible by a single tile should be matched by P. And that's actually the case, because if the way we define P here is by, by the matching, it's generated by a pair of 0 and 1 sequences producible by this match, by the tiles. So this F1 is true under A. F2 is also going to be true under P of A because F2 also captures this inductive construction of putting one extra tile to the beginning. Okay, so A satisfies F1 and F2. So what this means is therefore A satisfies F3. But if you look at F3, F3 say, what is F3? F3 said exists U, P of U and U. So there has to exist some elements in the underlying universe such that P should relate itself. So that means the P of A should be true under for some X of E and P X of E. Okay. Oh no. Yeah. For some X, which is a 0-1 sequence. And this is really coming from these facts. But then if we look at the definition of P of A, this P of A relates two terms. In other words, relate X and Y, which are subscripts of two terms, only when they can be produced by a sequence of tiles. So this really implies that X, there is a solution because it's both sides are the same as X. So this tells us that it's the solution to the given PCP problem. Okay, so that's, it's not a very hard proof, but it's a bit, yeah, it takes some time, although it's not a very hard proof. Okay, that's one direction which say validity implies a solution. Now for the other direction, which say if it has a solution that it is valid. So here's how you do it. So we have to show it's valid. We have to pick. So we assume. So it's a kind of sketch. So assume that the P has a solution. So then we have to show the F1 and F2 implies F3 is valid. So we pick structure A such that this structure A satisfies F1 and F2. Okay, then what we have to show, then we need to show A satisfies F3. So this is our proof obligation. Okay? This is our goal. Then how to do this? Then it turns out if P satisfies F1 and F2, okay, because F1 is really about the base case of, generating matching 0-1 sequences by tiles, and then this F2 is for the inductive case. If A satisfies F1, A is not a Hilbert structure. It can be any structure, but F1 and F2, in a sense, kind of axiomatize the idea of matching 0-1 sequences generatable by tiles. So if A satisfies this, then the following is true. This is a part which I'm not going to prove this, but I want you to think about this. And by this, the following is true. A will satisfy P of fx e and fy of e for all xy in the 0-1 sequence, as long as this x and y can be producible by tiles. Okay, there exist tiles I1, tile ID IM, such that x is the first component of the tiles and y is the second component of the tiles. Okay. So because of A satisfies F1 and F2, from there, this is true. A may relate to more terms, okay? But A at least make P relate, this type of pairs. A may make P true for more cases, but at least this is true. But then, now what they know is, by assumption, P has also let's call it PCP. So by assumption, we know that our PCP problem, the given PCP problem has a solution. What does this mean? This means there exists sequence I1 up to maybe IL, such that the x of I1 to x of IL and y of I1 up to y of IL, they are the same. These are the first and the second component of the tiles. Because this is coming from our assumption, which is say PCP has a solution. Okay. Now, if we bring these two things together, so we have something like this, and also we know that A is going to relate to ground term if these there are two ground terms can be producible by tiles. Okay. Now, if we put those two things together, then what we can say is A should relate to P f of x I1 to x of IL E and f of y I1 to y IL E. But these two guys are exactly the same U. Well, maybe not U. Say they are same. Thus, we can say A satisfies this is U, P of U, comma U, which is just F3. Okay, so that's how you can complete the proof. So they really I guess that's how we finish the proof. But the intuition behind the proof is really this implication F1 and F2 implies F3 somehow captures that our predicate P should at least true for matching tile cases. Okay, that's for the pair of 0-1 sequences producible by these tiles. If some structure satisfy F1 and F2, then that means such matching pairs of sequences should be related by P. Okay, so that's how we can complete the proof. And then actually the short argument of the proof is given to the slides. Now here's so this is what we proved. We show that P has a solution if and only if F1 and F2 implies F3 is valid. And here are multiple consequences. Okay, so what I want you to now is to use this fact, which is a PCP has a solution. We can have an encoding from PCP to the first order logic such a way that the P has a solution if and only if this translated formula is valid. Using this fact to show validity is undecidable and the satisfiability of first order logic is undecidable. So I will give you 1 minute to think about, 2 minutes to think about this. Okay, so the proof is really easy. I mean, we finished almost everything here. So we said, given any PCP problem P, so the first part is really easy. I mean, suppose the proof is by contradiction. If suppose validity is decidable, so which means that there is an algorithm. Let's call it AL, which take a formula and the terminates always and return the formula is valid or not. Now, using this algorithm, we construct a solution for the PCP problem. Then construct an algorithm for PCP using AL. Let's call it just spell. And how to do this? This new algorithm for PCP. It takes PCP problem P, and then what it does is that it just translates this P according to this proposition. And then we call this validity. Okay, so then it translates this, and then this proposition said the original PCP has a solution if and only if the formula is valid. So this will be the right, return the right answer for this PCP problem. But PCP is undecidable, which means that there can't be an algorithm, thus contradiction. So this means there is a contradiction. And the contradiction really happens because of our initial supposition. So initial suppositions, and then this contradiction say this cannot really happen. Now, for the satisfiability, here's how you can do for the satisfiability. So let's change this. So now do exactly the same thing, but with the satisfiability. So suppose we have satisfiability is decidable, and there is an algorithm that solves the satisfiability question, which let's call it set underbar. Then we can now construct the same way, the algorithm for PCP using this set underbar. How you do it? So we take PCP problem, we translate this, but then we add extra negation. And then we call set and put a negation again, okay? Then this one is a solution for the PCP. Why this is the case? I mean, this is the case, that's because if we translate this, then what we know is that if the negation of this translated part is unsatisfiable if and only if the original one is valid. In other words, original one is valid if and only if we cannot find a counterexample for its negation. Okay, so we are now asking, so this question becomes same as negation of F1 and F2 implies F3 is unset. Okay. So now we are calling satisfiability solver, but then the right answer should be about unsatisfiability. So we just put a negation outside. So we put the double negation there, initial negation, satisfiability, another negation. Then that will produce an algorithm for PCP. Same as before, PCP is undecidable problem, so there's a contradiction. And that contradiction is really about our initial assumption, which is satisfiability for first order logic is decidable. So this encoding from PCP to the first order logic kind of preserve the existence of solution, map existence of solution to the validity. And that shows unsatisfiability of first order logic and unsatisfiability of no. This is the undecidability of validity of first order logic, undecidability of satisfiability of first order logic. Okay. Now, here's a bit more interesting part. I mean, this is more interesting part, which is that what we have shown so far, we've shown so far, in a sense, tells us satisfiability for first order logic is actually more difficult problems than validity question. Okay, so we know that set validity of first order logic is semi-decidable. There's a semi-algorithm to check validity. This, let's call it first order logic. It's not decidable, but it's a semi-decidable. It's not decidable. Then you may ask, what about satisfiability of first order logic? Is it going to be semi-decidable or not? What we've shown above is that it's not decidable either. But you may say, oh, maybe satisfiability is just as hard as validity, so there may be some semi-algorithm which go into infinite loop. The formula is not satisfiable, but if it's satisfiable, it will produce the right answer. It turns out this is not the case. Okay, this is not the case. This is okay. It's okay, but this statement is false. So that's what this theorem is telling us. And then that theorem, in a sense, indicates satisfiability for first order logic is a more difficult problem than validity question. And now I will give you maybe 2 minutes to think about why that is the case. So this really, what the theorem is about is that we can't really even have a semi-algorithm for checking satisfiability. So think about this for maybe 2 minutes. Okay, so here's, I mean, if you took a course on complexity theory, you may heard some fact that some, let me just reduce the size of this a little bit. Some general result which say if something is recursively enumerable and its complement is recursively enumerable, then that thing has to be recursive. So that's, this one is related to that fact, but here's some another way to look at this. Essentially the same argument, but more in terms of the algorithm and semi-algorithm. So as I said, semi-algorithm means if the answer is yes, it will terminate and return yes. If answer is no, maybe return no, or it go into infinite loops. Okay, so possibility of going into the infinite loop in the negative answer case. So that's what makes some routine as a semi-algorithm. Algorithm has to terminate all the time. So now what's how to see this? Satisfiability is not semi-decidable. I mean, now suppose satisfiability is decidable, no, semi-decidable. So then we have a semi-decidable algorithm for satisfiability. Okay. Now, one thing we do know is that there exists, so this is coming from the supposition. One thing to know is that there is a semi-decidable algorithm for validity. I mean, this is what we studied so far, which is based on the ground resolution and so on. Okay. So this is, it's true. And this is what we learned so far. Okay, so now we have these two things. Then we can derive a contradiction to the undecidability for validity using these two guys. How to do this? Now, from using these two, we can build an algorithm for validity. So this will thus contradiction. So this will give a contradiction. So now why this is the case, why we can build an algorithm. The idea is to do the interleaved execution. So if we given a formula F, we want to check whether it's valid or not. But then there are two cases, whether this formula F is valid or formula F is not valid. But not valid means it has a counterexample. So this means that negation of F is satisfiable. Okay, so it has a counterexample. So what we do is that we run. So this is known fact. So what we do is that we design an algorithm that runs semi-validity check for F. And semi-satisfiability for negation of F. I mean, in an interleaved manner. What does this mean? This means that we are essentially running two programs. We run the first program, step 1, second program, step 1, go back to the first program, step 2, second program, step 2, and so on. So then if one of them terminates, okay, during this execution, then we say, okay, that's gonna be the output of our algorithm. So if this guy terminates first, then we say the result is valid. If this guy terminates, then we say the result is invalid. Now, because because there are only two possibilities, which is either formula is valid or formula is not valid. If the valid case is semi-bar is guaranteed to terminate. Invalid case semi-set, this second routine will be also guaranteed to terminate. This will always terminate, and we give the right answer. Okay, so this is the contradiction that I'm talking about. So if we have a algorithm for satisfiability, we can combine it with a semi-algorithm for validity to construct the algorithm for validity. And that can't happen, so that means this part, assuming that there exists a semi-algorithm for satisfiability, is wrong. I mean, it can't be the case. And as I said, this is a bit interesting because say that validity seems to be a more difficult problem, but it's actually an easier problem than satisfiability for first-order logic. Okay. Okay, so that's it for this set of slides. And does anybody have any questions about this? Yes, so there are some special cases. I think if you have a first-order logic with the two variables only, that's decidable, and so on. So there are many subfragments of first-order logic which have a decidability property. And later we will learn about some other fragments of first-order logic which is related to the arithmetic. And there are two kinds of axiomatization of arithmetic in first-order logic. One is piano arithmetic. The other one is called a Pressburg arithmetic. Piano arithmetic axiomatize addition and multiplication. Pressburg arithmetic only axiomatize addition part. Pressburg is decidable. Piano arithmetic is not decidable. So if you restrict the first-order logic and special case, there are decidable fragments. And also I don't think anybody in Kai study about this, but there are some logic. I mean, maybe not. It's not a first-order logic, but there are some logic called okay, let me just take, there are some other fragments which people exploit in knowledge representation. So so-called description logic in the knowledge representations, I think they are also using the decidable fragment of first-order logic. Okay, so then we will move on to the next. So next is about a resolution for first-order logic. Okay, so we studied about resolution, but then the resolution that we studied is not entirely satisfactory if we want to use what we learned so far as an algorithm. And I'm going to explain why that's the case, but here's just some rough idea. So if you just remember what kind of algorithm, maybe just show the next slide. So what kind of algorithm we're going to get based on what we learned so far? The algorithm say, given a first-order logic formula, we convert it to the score-lamp form for x1 to xn and g. And then we will consider, so and then g is a CNF. We will consider all the groundings of g. Typically, these groundings will be infinite. So there are some substitutions, another substitution, and so on. We just enumerate all these possibilities, which can be infinitely many. And then we try to derive a contradiction from finite subset of this. Okay, but now if you take a step back and think about this entire process, the first part is okay. I mean, so this part is okay. I mean, it's usually polynomial time. It's not a problem at all. But this grounding looks like a little bit not very ideal. Why this is the case? I mean, that's the reason is when we do the grounding, this which is replace variable in G by some ground terms. I mean, this grounding has no idea that we are looking for contradiction. Okay? So this grounding is just enumeration of all the possibility. Maybe if we do more clever enumerations, it's more likely to derive a contradiction from a few groundings instead of looking at 100 groundings. Maybe just looking at 10 grounding is enough to derive a contradiction. So we want more I mean, this is, so here in the slide we said it's, I mean, this entire algorithm or some kind of description of the algorithm based on the theory doesn't really tell us how we can do this grounding in a big clever way. Okay, so it doesn't say nothing about any strategy for grounding. So that's the situations. And based on what we learned so far. What we learned so far give you a way to design a semi-algorithm, but that's not ideal because the grounding it really doesn't really know what we are looking for, that we are looking for the contradiction, the derivation of contradiction. So then the question becomes, how can we do a bit more clever? Okay, how we can design some algorithm such a way that this grounding is somehow closely tied to our objective, which is to derive the contradiction using resolution theorem proving. So here comes what we're gonna study today, and also on Wednesday. And so we will learn about these things, especially the most important bit is something called unification. Okay. So we will learn something called unification, and then we will learn about so-called first order resolution proving. Okay, and then that uses unification, but what it does is that when it doesn't do grounding, but it does do something close to the grounding. But the way it does it is it does something on demand. Okay, so when it does the grounding, this grounding will be aware of the fact that we are looking for a contradiction. And here's some schematic description about what's going to happen, in this lecture. Okay. So in the here's a comparison between old semi-algorithm based on what we learned so far. And then here's some, just make more space. New algorithm. Again, it's a semi-algorithm, but new semi-algorithm that you will learn. So in the old algorithm, if you have a formula f, so say if you have a formula like this, x1, 2, xn, and g, then when we apply the resolution, okay, the goal of what this resolution prover, its job is mainly doing cancellation. So resolution proof step was, if you remember what it is, you have some literals L1 up to LK, and then they are all ground terms in the old algorithms. There is another things, but this time there's one negation of L1 and a bunch of stuff, and prime. So then when we do the resolutions, what the resolution does is that it cancel complementary literals. Okay. And then we bring these things together. We keep doing it until we end up with nothing. We end up with empty set of literals. So main purpose here is mainly cancellation. But in the first order resolutions, it does two things. Sorry. The first order resolution, it does in instantiating variables, which can be understood as something very close to the kind of, this is half grounding. And cancellation at the same time. So it does both of them at the same time. So the job of first order resolution is not just about doing cancellation. It also have to figure out how to replace quantified variables into some appropriate term. That term doesn't have to be grounded term. So that term will be generally contain other variables. but this resolution is, I mean, the old resolution, its job is doing only cancellation. New resolution is gonna use so-called unifications, and by using unification, it will do two things. One is instantiating some of the variables, or to quantify the variables, and then the other thing it does is that it does the user cancellation from old resolution. So it will do the two things. So this prover, the grounding and the cancellation is happening at the same time. Old style grounding happens first, cancellation happens next. In this new case, both of them will happen at the same time. That will make this idea will more suitable for the actual design of actual theorem prover. Okay, so let's see. So then the key concept, as I said, is something called unification. But to understand the unification, we need to remember or kind of need to be more familiar with this idea of substitution, because unification is all about substitution. So more generally, substitution can be understood as a mapping from the, so substitution is with respect to specific signature sigma, but substitution can be understood as a mapping from sigma terms to sigma term that satisfy these two properties. Okay, so it's a mapping from term to term, but it has to preserve constants. So for constant, it should be act as an identity. For functions, the term which is constructed by function application, it should be act as recursively. So the outcome should be the same as f, where the theta is applied to t1 up to tk. Some people call this type of property as a congruence. Congruence property. What this means is this substitution operator preserved the structure of, the kind of operations that exist in the that can be used to build the sigma terms. Okay. And then for substitution, I said it's a function. So typically when you say apply the function to something, you write it something like C and then return C. But so this is our notation to use the same thing, the function application in substitution. This turn out to be much more convenient to talk about substitution. Okay, so here are a few exercises I want you to do. So the first exercise is that now this definition, is a bit related, but not quite the same as the notion of substitution that you learned before, which is, we said substitution is just replacement of variable pi terms, okay? But it turns out these two guys are exactly the same. So the exercise one asks you to do it. So you say that if sigma and sigma prime are substitution that work the same for the variable, they are actually equal. So substitution is completely determined by what it does for the variable. So that's the first exercise I want you to do. The second exercise is that now suppose we express, so there are a few terminologies that I want to explain. There are these sigma dot sigma prime talk about a composition of substitution where we perform sigma first and then sigma prime next. As a function, if you view substitution as a function, so this sigma dot sigma prime, typically that's written as on some term t like this, which means that we, from term t, we apply sigma first and sigma prime next. We write it to the more conventional notation in the using function application. This can be written like this. So this sometimes is called diagrammatic composition because maybe because of this type of thing appears quite a lot in the category theory, and people use the word diagrammatic composition there. So anyhow, so this is a substitution notation that we're going to use quite a lot. The second thing that I want to tell you is we're going to use this notation like term. That's a substitution which replace map x to t, but all the other variables to itself. Okay, So it's a substitution that maps x to t or the very other variable to itself. And the way it acts on the terms is according to these two conditions that's described in the slide. Constant get mapped to constant. For function application, it worked as an inductive definition. Okay, so these are the two terminologies that I want you to do. We want you to be aware of. Then under this, then try to solve these 4 exercises in this slide. So I will give you maybe 5 minutes to solve all of them. So when I ask you to prove something, you can prove it if you want, but if you give a good proof sketch, that's also good enough. Okay, so let me show you the answer. And then for exercise 1, you can prove this by structural induction. So which means that you just need to prove the 3 cases for when we want to show that for each terms t, consider the 3 case scenario term is equal to constant c. So in that case, the substitution of t is the same as c of theta, c of theta prime, and t theta prime. And then for terms, if t is equal to variables, then t of theta and t of theta prime, they are the same by assumption. And then the third case, if term t is a function applications, t1 up to tk, so then we can use the essentially by induction. So you just use this condition together with induction, then that will allow you to handle this case. So that's how you can prove this. The second case, I mean, this is we already learned. I mean, it's essentially inductive definitions. So all the cases of most of the case, theta just get applied to the subterm. For instance, so it's an inductive definition. So, for example, if the formula F is conjunction, F1 and F2, then F applied to theta is defined by F1 applied to theta, F2 means theta get applied to F2. So that's what you have. In most cases like this, the only case that one has to be a bit careful is the quantification. So if F is universally quantified formula F1, so then if we apply the substitution, we have to be a little bit careful. So we said we want to apply substitution to F1, but we want to change the substitution a little bit so that we, for X, I mean, we just map X to itself. Because X is a bound variable by this formula, so we don't want to rename, well, we don't want to replace any bound variable. So for anything involving X, it has to be written, I mean, it has to be just act as an identity. Okay. But we are not, I mean, this is a general definition, but we are not going to actually use in this lecture. So okay, we are not much in this lecture. So I mean, related question is, this is same, actually this is no, because of this bound variable thing. If you think a little bit, you can come up with a counterexample. So I want to go into this exercise 3. For the exercise, it's quite easy. If this for this formula, if you apply the substitution, let's say replace x by f of y, so this outcome will be p of f of y and c. Compositions, if we do the composition, we can write this, I mean, using this notation. We first replace x by f of y, and then y will be replaced by this guy. So in this substitution, x will be replaced by this, and then y will be replaced by c of z and 1. So we replace x and y, x will be replaced by this, y will be replaced by this. Okay. And if you just apply this substitution, you can get an answer for the last case. Okay, so before finishing, let me just mention quite important concept. Right. And then I will go through this again, but here's a very important concept which will play a prominent role in this set of slides and in this first order resolution proof. Okay, the concept is the idea of a unifier and the most general unifier. So then that concept appears in the context where we have a set of literals. If I give you a reminder of literals, literals are atomic formula, which is either propositional variable, no, predicate variable applied to some t1 up to tn. These t's are not necessarily ground terms, so they may contain variables. Also, I mean, typically true and false, but usually, I mean, these guys are all eliminated. So typically, I mean, true, false, and the p, all of them are considered as atomic formula, but when we talk about the set of literals, we mean this atomic formula or the predicate applied to term t1 up to tn or its negation. So that's what we have. So these are the much simpler formula than general first order logic formulas, almost like propositional logic formula. And then we define this idea of applying substitution to this set of literals by just applying substitution to every literal in the set. Now, there's an important concept is that if we say this substitution is a unifier for a set of literals, if after applying the substitution, this set of literals becomes a singleton set. Everything in the set becomes the same. Okay. So the example that I showed you in the slide is this. Suppose think about substitution theta that replace x by f of a and y by a. Okay, and that is a unifier for this set of literals, which contains two terms, not two terms. It contains two literals. If I apply the substitution theta here, x will be replaced by f of a. So this x will be replaced by f of a, and then this y will be replaced by a. So then they become the same because this will become a, and this will become f of a. So both will become the same. So which means that theta is a unifier for this set of literals. Okay, but another, this unifier doesn't have to be unique. There can be another unifier theta prime in this case, which replace x by f of y. If we do so, then in this case, we apply the prime, the outcome is going to be p of f of y. And so unifier doesn't have to be unique. It can be many. But in some sense, there are ways to compare which unifier is better than the others. And that's given by this relationship. If you compare these two unifiers, theta prime and theta here, in a sense, theta is more specific than theta prime. So theta can be obtained from theta prime by applying one more substitution, which is replacing y by a. Okay? So and that more formally, that can be expressed by this relationship. This relationship say, the substitution theta is obtained by first applying substitution theta prime, and then applying another substitution, which is replacing y by a. So we use the word and said the following phrase, which say theta factors through theta prime in this case. So if theta factored through theta prime, that means theta is more specific. So if both theta and theta prime are unifier for the set of literals, then in some sense, theta does a lot more than what's necessary for the unifying everything. So it becomes make things more specific than what's absolutely necessary. So that gives us some comparison. So some people design an order, some kind of order, and say this theta prime is less than theta, to means that theta prime is less specific than theta if this relationship is true. Something like this relationship is true. And that brings to the next concept, which will play a very prominent role. We say that theta is the most general unifier for a set of literal D if it satisfies two conditions. First, theta has to be a unifier. So that's a condition one. And then second, it has to be, in a sense, best unifier according to this factor through relationship, which means that for any other unifier theta prime, that theta prime will factor through theta. In other words, there should exist another substitution theta double prime such that this relationship is true. In the less than notation that I just wrote over there, theta should be less than equal to theta prime, okay? Because theta prime can be obtained from theta and then another substitution theta double prime. So this is the most general unifier, and that will play a very important role in the lecture on Wednesday. Okay, so that's it for today, and we will go over this idea of unifier and most general unifier again, and then continue to talk about this first order resolution prover. Okay, that's it, and thank you very much.